Okay. As usual, we'll give it a minute for everyone to show up here and for me to pull out my trusty tablet. Maybe we won't have anyone show up. Actually, it is Friday night. All right. Oh, gonna have to run that script quick for my tablet. Okay, come on now. Okay, so it looks like we've got a couple of folks here. Just a quick reminder, if anyone has not, hopefully no one's forgotten, the first homework is due tonight. Toss it on the class WYO courses page. Here, I'll pull it up just in case. I'm sure everybody knows how to do it, but just in case you don't, let me bring this up real quick. It's going to give me a second to type my password off screen here. There we go. All right, let's see. So if you're in the class complex analysis page, I will go to a student view here so we can see it. Go to assignments. You'll see homework number 1. You can start assignment, and all that means when you click start assignment, or it doesn't matter if you click start. I actually don't know if that matters at all. I don't know what that button does. It's actually a great question. What on earth does start assignment mean? Whatever. Either way, you upload a file down here. You choose your file and you upload it, and you can Asimov. Sorry, my dog is barking up a storm at nothing right now. Anyways, you upload your file, take pictures. You can do another file if you want. If you've like handwritten it, you can take high quality pictures of your homework and send it in. If you've typed it, you can submit a PDF. You can scan it, whatever you like, and I'll be able to annotate things there. So easy enough. Should be pretty simple and straightforward. You have until 11:59 p.m. tonight to do that, and then it will automatically kick out the key, so you can see all of the answers fully worked out, and check your work against it. So not too bad. All right, let's see if this stupid thing is. What is wrong with it? Sorry, folks, I'm having a minor technical difficulty with this tablet. If I can't resolve this pretty quickly, we're gonna have to. Oh, there we go. Good. Okay. Oh, yeah, it's a little bit messed up. All right. Let's see if we can run this script again. Okay, good. We are back in action. All right, so I fixed that thing. Nice. What a beast. So if you recall, at the end of our last lecture, we were going through proposition 1.25, and we had a couple of items that were left to talk about. So I will try to go relatively quickly through any of this. Just these last ones, they're very useful. I definitely recommend going into your textbook and looking through the proofs it presents for them. They're very fun, classic proofs that you'll find in a lot of different places. The triangle inequality, number 5, this guy right here, it's the triangle inequality. This one is the reverse triangle inequality. And then finally, a version of the Koshi-Schwartz inequality. Koshi-Schwartz. Or if you prefer, Koshi-Bunyakovsky-Schwartz. Depending on whether you want to, whether you hold any Cold War era grudges against Russian mathematicians. Great, very useful results. You should just embed these things into your knowledge. You should just not even have to prove that these are true. You should just see them and almost feel that they are true in your bones or something folksy like that. And let's talk a little bit about why with a couple of them at least. So, first one, 5, triangle inequality as it's called, is actually pretty straightforward to see. So here I'll draw ourselves a little plane here. And I guess I could have made that a different color. It doesn't matter. So suppose you have, say, Z right here, and then I'll get a different thing. Maybe I'll make like a W. There we go. All right, let's call this Z prime. And let's call this other guy Z. These little, so we're in C right now, of course, just writing things as vectors. Naturally, if we're doing this, we can always take a sum, and I'll try to make this as close as possible. The nice way to add things together, you can think of Z prime plus Z as being this nice just tip to tail, or tip tail to tip, whatever you want to call it. So this would be Z prime plus Z, or Z plus Z prime, whatever you prefer. This green one right here, I should maybe have used a different color than green. It doesn't matter. Anyways, what 5 is saying is that the length, the magnitude of Z plus Z prime is less than or equal to the sum of the lengths of Z prime and Z. This is pretty obvious. It is equivalent. Just looking at what we got right here, imagine taking this little thing and just flipping it. What this statement, this triangle inequality piece here is saying is that in C at least, the shortest distance between 2 points is a straight line. That is, if you're going from, let me put this, make sure I have a different color. If you're going from down here to up here, it is definitely shorter to go along here, Z prime plus Z, than it is to go Z and then Z prime. See what I'm saying? Definitely a lot easier to see this visually with going down paths. The reverse triangle inequality is just essentially the opposite. And I definitely encourage you to sit down and try to do the reverse triangle inequality if you have never seen it proved before. It is remarkably easy, actually, and kind of a fun little trick. But basically, this gives you a bound on the length of a difference, right? This gives you a upper bound on the length of a sum, while the reverse triangle inequality gives you a lower bound on the length of a difference. And it's pretty nice. It just says that the magnitude modulus absolute value of Z minus Z prime is greater than or equal to the absolute value of the modulus of Z minus Z prime. This is not particularly surprising. Basically, it says that in the worst case scenario, you can get 0, right? Because this is all an absolute value. You definitely can't get anything lower than 0. And you can definitely get 0 when Z and Z prime have the same length or are exactly the same, right? If Z equals Z prime, then this is 0. And then on the other side, well, of course, they have the same modulus and it's 0. However, since we're sitting in C as opposed to just in the real line, or something more simple like that, you can have things that have the same modulus that are not the same. So for example, just imagine instead of Z, and you can look at minus Z. That obviously has the exact same modulus magnitude as Z, right? So in this case, it would say that the modulus of their difference is greater than 0. That's certainly true, but it gives no upper bound, right? It just tells you how far away it could be. and it's a pretty natural one. You can use 5 to prove 6 very easily. You just basically replace one of the values with a difference itself, involving the other one. The final piece right here, the Cauchy-Schwarz inequality is great. It is phrased in a way that I think makes it look much more complex or difficult or interesting than it potentially is. It is a very good result and it is super useful. And we should use it with great frequency whenever we get a chance. But, and I won't spend much time on it. Are you familiar, if you're familiar with the dot product, which I'm assuming everybody is, considering that I think you've all taken Calculus 3. I'm imagining a lot of people have taken linear algebra as well. Remember that the dot product is just component-wise multiplication and then summing up the results, right? So this first little piece right here, you can think about it like z1 down through zn, this like vector in n copies of C, dot product, w1 through wn, yeah? Okay, dot product right there. And we're saying that that's less than or equal to, well, if you go through and you're squaring and adding all these things up, what this is this is just the length of these vectors, the length of this guy and the length of that guy. I think you've also seen this in linear algebra or in Calc 3. This is if we want to, we call this guy right here. Oh, I'm going to use a little bit of, well, whatever. I'll just do some annoying notation right here. I'll do double bars to mean length in this case. The norm, as you might call it. The norm of this guy times the norm of this guy. So W1 through WN. So double bars meaning length, right? It's saying that the dot product is less than or equal to the, and I guess I should be careful here. I should say the absolute value of the dot product is less than or equal to the product of the lengths. And this isn't too weird. Think about, well, depending on what you've done in linear algebra, you may know that you can actually, but never mind. We won't. I don't want to delve too deeply into any linear algebra things since it will just distract from the topic. But basically, all that's going on here is we're getting a relationship between length and some notion of angle. Nothing too fancy. If you want to kind of get an intuition for what this is like, just imagine if W1 was, say, equal to Z1, then I'd have Z1, so it'd be Z1 squared all the way up to the last bit right there, right? Okay, so this would be, we're basically looking at these terms right here, and then it would be the same again, and so it would just be, okay, well, multiply the same thing twice, and you just get the same thing on either side. What you can kind of think about is like, it's like taking, this is the easy way to remember it, at least, if you want a quick idea of that. So I'll just write it. If, or I'll even write if WK equals ZK, this says that the sum of the moduli of the z's squared is less than or equal to, and I should put it like this. So if you had both of these the same, you can just imagine the square root drops out, right? It says that the moduli of the sum of squares is less than or equal to the sum of the squares of the moduli. This isn't too surprising at all right there. So that is just basically what you can think about this guy as being a more advanced version of this little thing right here. All right, fair enough. Whatever. We'll move on from this point at the moment, but you should go check in your textbook if you've never seen a proof of the Cauchy-Schwartz inequality. I encourage you to view a proof of it. It is a good proof. I believe they present a variational proof right here in the textbook, which is IMO, the best type of proof for the Cauchy-Schwartz inequality. I wish they would have introduced inner products and something like that here, but it does save us some time to not have to deal with all that. All right, so we will move on now from this section and begin to talk a little bit about some elementary functions. We would normally do a few more exercises, but since I think we've pretty well exhausted 1.2, it's worthwhile to get on past some of these basic properties into a little bit more of the fun stuff. We'll have lots of opportunities to use all those properties as we go. So 1.3, some elementary functions. This little section is excellent, so because it will introduce us to a number of really useful ways to think about things, and some of the intuition for a lot of what we'll do later and the approaches that we'll use. All right, let's start it out by recalling some stuff that I bet everybody knows. Whether or not you remember it super clearly right now, don't worry. So recall. So we're going to recall really quick and try to remember something. Does anyone remember the Maclaurin series, the Taylor series centered at 0 for sine x? Is it something like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot, you know, so on and so on, right? Everyone remember that, right? Similarly, for cosine, we had 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus yada yada yada, right? The good old-fashioned Maclaurin expansion of sine and cosine about 0. All right, good stuff. This is a great little formula that we're going to use quite a bit here. You also remember that e to the x had a nice series representation, and its representation was just 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial and so on, right? Okay, so these guys, we're going to recall them really quick in case you forgot them. And we're going to use this to inform the way that we should and will make the complex analogs of these functions. So this is kind of going to be one of the main focuses of what the beginning of this class is. It's a very simple question in some ways. The question that we're going to ask is, the following: what are the complex versions of familiar functions? And how do we know? Well, on one hand, this question is silly because it supposes that there just is a complex version of a familiar function. There are functions on C, so functions that send C to C, that may agree or disagree with various things and have certain properties, whether we call them the complex versions of a familiar function is sort of up to us. But intuitively, we all know what this kind of should mean. What we want is we want functions f of z that agree with a familiar real valued function. We'll call it f of x, abuse notation slightly. Or if I want to be a little bit better here, we'll do it like this. F of x, when z has mz equal to 0. We probably want that. Seems fair. So the kind of idea here, and I maybe should use different notation, but we want f tilde such that it agrees with f of x when z has mz equals 0. So something like this is reasonable. Basically, the idea, if you want to think of it like this, is that i.e. something along the lines of like f tilde of, I don't know, x plus 0 I equals f of x, right? And this is not truly correct if you actually think about it. It's basically what you want, but ultimately, if we're looking for complex valued functions, in this case, what I should be writing and what I hesitated on earlier is that I'm really looking for something from C to C. And we have functions f from R to R such that the embedding iota, we'll call it, from R into C, where iota of x is equal to x, since every real number is also a complex number, right? We want things so that f of f composed with iota is equal to f tilde restricted to, or sorry, did this backwards, oops, f tilde composed with iota is equal to f, right? So if I take this little adapter, go from R over to C, and then C over to C, and then maybe I should be clearer here because we also need to send f over into C. We could, I mean, it's ultimately, whether we want to say that this goes to C or use multiple different inclusions is not too important, but you get the gist of it. What we're technically asking, if we want to ask it in like very clear terms, requires some additional inclusions. Don't let any of that nonsense, not that it's irrelevant, but don't let any of that throw you off for the moment. It's the obvious thing that we're looking for. We're looking for things so that if we plug in just real numbers, we get out the usual stuff that we're familiar with. Yeah, all right. So let's start with a good one. Let's start with e to the x. So as we can recall earlier, we remember that e to the x has a Maclaurin series that looks like this. It's 1 plus x squared over 2 factorial and so on, right? So we have that e to the x, if you recall, is just the sum from k equals 0 to infinity. And we're going to be a little bit silly here for a moment, but not quite yet. Of x to the k over k factorial. And then what we're going to do is we're going to take this piece here, and this is the part that's maybe silly, and we're going to try turning this into e to the... Let's try plugging something in here that's complex. But in some sense, like it's like we know how to plug numbers into complex numbers into a polynomial like this, right? we could take a complex number squared, right? We've done that before. And so it sort of feels like we should be able to do something like this. Let's do like e to the, let's do iy, right? Well, then we're going to get the sum from k equals 0 to infinity of iy to the k over k factorial, right? Okay. Nothing too crazy yet. And if we do this, we can start to see something nice happen. What I should say is that we need to be very careful here because it is not remotely clear that this should be right. It should mean anything, that this is a correct or reasonable thing to do. We haven't defined what it means for a series to converge in C yet. And that is very important. We should not take notions of convergence to be a given. They're something that requires careful thought and gives you a number of different things depending on what you are looking at in terms of your type of convergence. There are more than one ways that you can have things converge. So this is purely heuristic at this point. But let's go through and let's actually try plugging things in, and I think you'll see that we get something very familiar and useful. So if we go on through and we start to do this, what we'll see is we'll get 1 because that's not going to change. We get iy over 1 factorial, which is still just 1, right? Then we get, well, iy squared over 2 factorial, which is just 2, iy to the third, and so on, over 3 factorial. And then we keep going, dot, 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 forever, right? Well, what do we get? We have 1 plus iy over 1 factorial, right? Minus y squared over 2 factorial plus, or should we go minus here? Depends what you want to write. But I'll write iy to the third over 3 factorial. And then we're going to get minus y to the fourth over 4 factorial plus, and so on and so on. It's pretty easy to see what we're starting to get. Let's just take pieces that involve i's and those pieces that don't. We have 1 minus y squared over 2 factorial minus y to the, make sure I'm writing this right, or did I do this wrong, or should that be plus? What have I done wrong? I've just made a mistake. Oh my god, I'm an idiot. Minus right here because of that I getting cubed. I'm an idiot. Sorry if I just messed anyone's intuition up right there. I'm going too fast. This should be a minus and this should be a plus. I forgot to take the i's into account. When you cube I, you'll get I squared times I, so that's minus I, right? And then when we get to the fourth, minus I times I is just going to be 1 once again, and so that's positive, and then it becomes negative. You get the idea, right? My bad there, writing a little bit too quick for my own good. We're going to be switching back and forth in the good old-fashioned regular way. Let me make sure I'm on track there. 2 minus y over 3 plus y over 4 plus y over 5. So yeah, it'll be minus minus plus plus minus minus plus plus. That is what we want. Minus minus plus plus. Yep, there we go. Okay, perfect. Sorry, gotta double check the detail there. You know how it goes. Just writing too quickly and you can make mistakes. Y to the fourth over 4 factorial. And then we get a minus, right, and so on and so on. You got this chunk, and then all of the rest of the pieces have i's in them, right? So plus I, and then we're going to have, well, y minus y to the third over 3 factorial plus y to the fifth over 5 factorial minus, and so on and so on. Sorry, so on and so on. Notice what this is. This is just the Maclaurin series for cosine of y. That's this chunk. Plus I sine of y. Oh my God, look at that. How about that? Isn't that a pretty good trick? If that should be a fun reveal. I apologize if I ruined anyone's fun by flipping a sign right there. Anyways, cosine y plus I sine y. And hey, would you know it, while we are not fully justified, we are just doing this intuitively as a heuristic right now for e to the iy. It seems reasonable to just take this series representation of the regular old real valued function, try plugging something like this in there, and getting something like this out. That is, as long as convergence in C works sort of the way we want it to, as you might expect that it probably ends up being the case, then we should be able to do things like this and get out reasonable representations for things like e to the iy. Okay, now we'll probably also want, so let me just rewrite this little thing we've just discovered. So we could reasonably say e to the iy equals something like cosine y plus I sine y, right? We can't reasonably say in the sense that like this is true at this point. We haven't like proved it to be the case. We haven't described what it means, but at best we could reasonably define this to be that. But we will eventually later show that there is a good notion of convergence in C, and that the function that we're defining now works this way. So we could say something reasonably like this. And if we want, e to the a plus b to equal, say, like e to the a times e to the b, then we have e to the x plus iy equals, well, e to the x, e to the iy, and hey, wouldn't you know it, that's e to the x times cosine y plus I sine y. Hey. This now covers all complex numbers. Z equals x plus iy in C. Hey, how about this? How about this? We have just kind of independently sort of come up with a reasonable candidate for the complex analog of e to the x, of the exponential function. And what we got is just e to the z is e to the real part of z times cosine of the imaginary part plus I sine of the imaginary part. Oh, okay. This is interesting. This is not necessarily that weird, but look at what the heck our reasonable candidate for a function for e to the z will let us do. For example, let's do e to the I pi, a transcendental number to the power of an imaginary number times an irrational number. Okay, e to the I pi is just, well, what is the real part of this? What's the x business in x plus iy here? Well, it's 0, right? E to the 0 cosine of, well, y is now pi in this case, right? Cosine pi plus I sine pi. Oh, what is this? Well, e to the 0 is 1. Cosine of pi is -1. Sine of pi is 0, so this is just -1. Hey, this is the famous supposed, people like to say like, oh, best, most beautiful, whatever. I don't know why they do it. Euler's equation, e to the I pi equals -1. How about that? A transcendental number to the power of an imaginary number times an irrational number is equal to -1. Doesn't that seem strangely complex on the left-hand side, but surprisingly simple on the right-hand side? Don't you feel a little bit satisfied by that? It's kind of fun. And indeed, this is how this was done in the first place. This is what goes into this fancy, much beloved, for some reason. It was historically important to understand the complex exponential function. But this is what goes into that oft-quoted result. Granted, there are technical details that we are brushing under the rug that we will get to in Chapter 3 regarding the convergence of series in C and what it means for the infinite series that we're manipulating willy-nilly right here to converge. This is not necessarily immediately clear, but we'll get into that in a bit. But assuming that everything goes right there, we have now defined the complex exponential function, and bada boom, we've got it. We've got cool results like this. So this is now the definition. E to the z, e to the x plus I y is e to the x cosine y plus I sine y. We'll proceed with this as the definition for right now, and it will do us well. So that is the starting point. Your book, I think, I'm looking right now. They also give you another way to get here. Yep. Okay, I'm going to skip this because I think that while it is a cool way to do it, it is not nearly as well motivated as this little piece. This little piece right here that we've just done, I think, is so kind of straightforward that you don't really have to suspend your disbelief much. It doesn't trick you. All you have to do is assume that there is some kind of a reasonable notion of a power series in C, and you can define the thing you want to define. You get a good candidate for it at least, right? But the other one they use involves certain unique solutions to differential equations, and what I think is, maybe you totally disagree, and if you do, all the more power to you. You have intuition for things that I had no intuition for when I first learned this. But it tries to show that, hey, if these regular good old differential equations have unique solutions, then so should the complex analogs, and that tells us how to make it. It's a cute little argument. It's a great trick, but I think that unless you have I personally didn't have a lot of good intuition for the fact that solutions should be unique to differential equations in C. I think that requires a heavier amount of machinery on a theoretical level and a greater level of intuition for how things involving C behave than the idea that we might be able to define a notion of convergence. So that's why I think that this one is better. Your book does a different presentation, though, and if you want to look at it, I do recommend it. I think it's cool. So there's a whole bunch of different things we can go through here, a whole bunch of different facts involving this cool new function that we've made. In particular, this e to the z is periodic. That's kind of cool. And just to be clear, we should define that. So I'll do a quick definition. So a function from C to C is periodic if there exists W in C such that f of z plus W equals f of z for all z in C. Now, if I'm writing this relatively quick, this will save us a few words here and there. You've probably seen it. This backwards E means exists, and this upside down A means all. Look how quick it is to write things instead of saying for all or if there exists. It'll save us a lot of little things. Obviously, this ST means such that. So this is also in your book. I think it's on page 27. So periodic functions, notice just from our definition right here, right? Because cosine and sine are periodic in the regular old sense of just being periodic, they're the nice little waves. If you add multiples of 2 pi to y, you'll get the same things, right? If you go around the unit circle to the place you were at, you can always do that. So e to the z is periodic with periods. That's what these w you might call right here, the w's, right? With periods of the form 2 pi ni for integers n. So multiples of 2 pi in the y slot. You can always throw that in, and you won't get anything different. But that is a useful little trick, and I will throw on the screen here a number of nice little properties about our cool newly defined function that we're all so proud of. We will briefly kind of touch on a few of them, but we won't prove them right now because there are so many things in this chapter to go over that are worth seeing, and we have got to get to them. Oh, what have I just done? There we go. I believe I made a small mistake. Let's see. Oh. Make sure I got this at a good resolution. I always want to paste these things in beforehand, but whenever I do, then I end up constraining the available room I have to write, and it makes it much worse to try to read along. All right. There we are, and I will jump this paint layer right up. Okay. So this proposition 1.32, very useful, full of lots of great information. These nice facts, like, you can have exponentials act in the way you want. It's never zero. This is pretty obvious just from the fact that I'll write it down here just to avoid scrolling again. Remember, we're, actually, I'll write it up high. Remember, e to the x plus iy, e to the z if you want, is e to the x, regular old real exponential, cosine y plus I sine y, regular old real sine and cosine. Drew that C very badly. Anyway, regular old sine and cosine, regular exponential on the right-hand side. So this guy is never zero. That's pretty obvious just because e to the x, real valued function, that's not zero. And then that cosine plus I sine, you're never going to get sine and cosine simultaneously zero. Just think about the unit circle. There is no point on the circle that has an x and a y coordinate of 0. That's in the middle of the circle. So obviously this thing will never be 0. Okay. If x is real, then e to the x will be greater than 1 when x is greater than 0. That is very obvious from our definition we've set up here. And e to the x will be between 0 and 1 when x is less than 0. This is also obvious from the definition we set up. The modulus of e to the x plus iy is equal to e to the x. This is slightly more interesting. Why is this the case? Well, just think about cosine y plus I sine y. Well, we're just looking at points on the unit circle right there, yeah? And so the e to the x piece is the multiplier. So that is the thing that determines how long long the thing is, right? The cosine y plus I sine y basically just determines which which good point we are at on the unit circle, right? So this the angle of y determines where we're at on the unit circle. And we're like right here. And then the e to the x tells us how far we're stretching it, whether it's going to be like way out here or if it's going to be like really small and just barely like that. See what I'm saying? I'm drawing that real small there. So that's pretty standard. You can just imagine it geometrically. E to the I pi over 2 is I. E to the I pi is -1. E to the 3 pi I over 2 is minus I. E to the 2 pi I is 1. Hey, do you notice those from anywhere? Are those the fourth roots of unity? Ho, what about that? It looks like, oh man, looks like fractions of pi I are roots of unity? That's pretty cool. All right. E to the 2 pi I, whatever, right? E to the fraction of 2 pi times I, that's the root of unity. So, bam, nice tie-in. Okay, cool. You can compute those the same way we did the e to the I pi, e to the pi I, E to the z is periodic. Each period for e to the z has the form 2 pi ni for some integer n. That's what we were just talking about. E to the z equals 1 if z is equal to 2n pi I for some integer n. This is more interesting. So this is kind of obvious if you sort of think about it. Namely, if if it's not, it can't be 1 if x is not 0, right? X kind of has to be 0. Otherwise, this will be, e, a number that is bigger than 1 to the power of something that is bigger than 0, right? If it's negative, it'll be flipping in the fractions and all that stuff. But this last piece probably has the most actual little things to go through and actually double check for reasons that are probably kind of obvious, that you have to actually make sure that you don't get 1 from some other combination. But basically this is saying 2n pi I positive, negative, or 0, right? So it's saying one side or the other side, just basically at this little chunk right here, just going to be 0 right there, and that's what's going on. All right, cool enough. We'll just leave it there for now. I don't want to ramble about this piece too much more because we have many more things to cover. This proposition is useful, and we will use it in many other places. I think that you should go look at that. And actually, I will. We have enough time. It's not going to cause any problems. Here, this guy right here. Let's just do this last one because I worry that I haven't given a good intuition. So we do know that e to the 0 should be 1, right? Just look at the definition. E to the 0, this piece will be 1. And then since we have 0 and y, cosine of 0 plus I sine 0, well, you'll just get 1 right there, and this piece will be 0. Okay, so you get 1. We know that. Okay, so we also know that e to the 2 pi ni, this thing should be 1 as well, right? Because, well, we're just going all the way around the circle in the complex piece. And, multiples of 2 pi, same as being at 0 in terms of sine and cosine, right? Okay, so we should get 1 there as well. That's fair. Now, using the periodic nature, which we've already talked about, then think about this. So if e to the z is 1, well, e to the z plus z prime has to be equal to e to the z prime for all z prime. Do you agree with that? Yeah, that seems reasonable, right? So we can use the fact that it's periodic and has this period of the form 2 pi ni, and we can use this fact to say that z prime must then be 2 pi ni, right? Does that make sense? This is basically the argument, so we can probably leave it there for right now. Okay, so let's keep it going, and let's talk a little bit about the polar representation of a complex number. Namely, not to dwell too much on the properties of e to the z, we do also remember, though, we remember that we could write z equals x plus iy, and we could also write z equals r cosine theta plus I sine theta, right? Where theta is arg z and r is the modulus of z. But wait a second. What is this little business right here? Wait a second. So this is saying this little chunk right there is saying that so z is given by, well, let's just write it mod z right there. And then cosine theta plus I sine theta. Well, wait a second. This is e to the I arg z. Oh. How about that? Now I've just written every complex number in terms of its modulus times a e to the I something. Kind of cool. And hey, in some sort of sense, you should get, and I want to be very clear that we don't really have a complex notion of the logarithm yet. This will be one of the more interesting ones to define. You could, of course, get this modulus z, assuming it's z is non-zero, in terms of e to the something, right? But if it's 0, then we can't, so we might as well just write it like this. Namely, you do it as e to the log modulus z for z not equal to 0. I won't actually write that now because I don't want anyone to assume that that holds in a situation where it doesn't, like when z is 0. This is probably a better formula because it actually holds for all z in c instead of all z in c except 0. All right, fair enough. Now, one thing that is going to be useful to us is the rest of the trig functions. So we have e to the x plus iy given by e to the x cosine y plus I sine y. All right, fair enough. Now, what about sines and cosines? Well, we should just be able to go through and kind of solve some stuff, right? We could just say, okay, let's solve for sine. Let's and I'll kind of save us the trouble here. Let's do sine y is going to be equal to e to the iy minus e to the minus iy over 2I. This is relatively easy to see. If you want to go through and prove it, which we will just really quickly just for convenience, e to the iy is just going to be, well, cosine y minus, plus I sine y, and then minus e to the minus iy, so that'll be cosine of minus y plus I sine minus y, right? And this all over 2I. And if you go through and you actually do this, well, you get cosine y minus cosine of minus y, but cosine is even, so this is minus cosine of y. Okay, then we get plus I, and I'll factor out the I. Actually, I won't even factor out the I. I'll leave it, whatever. Sine y minus I sine minus y, so that's minus and minus, that's plus, right? Plus sine y. And then this will be all over 2I still. And hey, wouldn't you know it, these guys cancel. Now I've got 2 sine y or 2I sine y over 2I, and that's just sine y, right? Hey, good enough, good enough. Okay, so if you are cool with that little chunk right there, and you can assume that you can do the same nice little thing for cosine, I will now just erase this little piece to save us some room and not have to scroll around too much, and do exactly the same for cosine y, and you could do this, solve it out, e to the iy plus e to the minus iy over 2, basically the same formula, you just don't need this minus, and you don't need the I on the bottom. Okay, fairly straightforward, and we could imagine, perhaps, we could take sine z to be e to the z minus e to the minus z over 2I or something, right? Does that seem fair? Something to that nature? And then we could take cosine of z to be e to the iz plus e to the minus iz all over 2. Something like this? Yeah. All right. So this is a good candidate for what we might want the complex trig functions to look like. And then we could define the rest of the complex trig functions just in terms of these guys, and it will be cool. So once again, this is not anything other than intuition for how we should get these things. The true justification that comes from proving that power series exist in the world of the complex numbers and what the heck that even means will come later in the class. But for right now, this is a great place to stop. Next time we will investigate some properties of the complex trig functions, see that some of the familiar ones carry on through, and go into other elementary functions like the natural logarithm. All right, cool. It is Friday, and so I imagine you guys probably want to head on out. So I think I went actually slightly over. My apologies. Let's just call it quits for the day. If you have any chat or questions, throw them in the chat and we can answer them. If not, I can answer them by email later. And remember to submit your homework tonight. Cool. I'll wait around for a minute for questions, but otherwise we're done for the day. All right. Doesn't anyone have any questions in the chat, or should I end it? Going once, going twice. All right. Have an awesome weekend, everybody. Bye.